Well, thank you for coming to another lecture for interactive computer graphics. Now, today's lecture is going to be an important one. We're going to talk about a very, very important topic in the context of not just interactive computer graphics, but computer graphics in general, but definitely interactive computer graphics as well. So you will see that I'm going to be recycling some of my old slides. And this is probably going to be the last lecture that I will be recycling any old slides. But it's not going to be completely old slides, so continue paying attention. There's going to be new stuff here. All right, so our topic for today is, drumroll, the rendering equation. Yeah, very, very, very important topic. Now, Jim Kajiya in 1986 wrote a paper called the rendering equation. That sort of provided a mathematical foundation of what we have been doing in computer graphics. Now, Kajiya is saying, this rendering stuff that we've been doing, we've been actually trying to solve this equation, the rendering equation. So it sort of provided this mathematical foundation of rendering we still use today. So this is a very, very important topic of understanding everything about rendering. And so like all the stuff that came before that was sort of a little bit incomplete in that sense. And everything that came after this rendering equation sort of relied on the rendering equation. So everything we do about rendering is really related to this topic. So that's a very, very important topic, very, very important thing for you all to understand. And I will break it down for you today. That's the plan. Now, this is the rendering equation. Lovely, isn't it? Now, if you've never seen this before, it might look scary. And yeah, well, there's an integral, there are all sorts of symbols, which is normal. But when you understand this, you will see that this is actually something very simple and really beautiful and explains this complicated process of rendering really well and summarizes it really well. So let's dive into it. But let's start with something that's a little bit more familiar to us. Now, we talked about Blinn and Phong material models, right? Remember this equation? We've even implemented this. This is the Blinn-Phong shading model. The only difference between Blinn and Phong in this case is just how the angle, this angle phi is defined over here, right? Beyond that, they're basically using the same equation, these two material models. And these are our material properties over here. And this is our equation. Now, we talked about something that you will remember, this cosine term here. Do you remember what we called this? We called it the geometry term. And the geometry term was a function of the incoming light to the surface. So it really was supposed to be next to the light source. So we had this hidden divide by cosine theta in here in the specular term. And this geometry term, if you'll remember, is telling us how much light is arriving to the surface based on the light direction and the orientation of the surface. So if I take the surface and rotate it, the amount of light per area that I'm receiving gets less and less, and so the surface looks darker and darker. And as the light direction is aligned with the surface normal, I'm getting the maximum amount of light. And we try to look at this in this 2D cross-section like this. We looked at a beam of light hitting the surface, and we said that if this beam of light is hitting this unit area on this surface where the light direction is aligned with the surface normal, as I rotate this surface, this beam of light, the same beam of light, will be illuminating a larger area on this surface, right? So that means that it's the light energy is spread out to a larger area. That means the light per unit area on the surface is going to be less. And that's related to this angle between the light direction and the surface normal, angle theta. More specifically, cosine theta gave us exactly how much light was spreading on the surface. So this cosine theta term here is our geometry term. It's just about how much light is coming in here. Now, this rest of the stuff, this stuff here, this is the material model, So it's a very specific material model. It's using these material properties. Both Blinn and Phong are using the same formulation, but they're sort of defining this angle differently. So they are actually two different material models. In general, though, Blin and Fong are just examples of some simple material models. There are various material models representing different types of material behavior. So our goal here is to sort of define how this surface that we're trying to render is reacting to the incoming light. So in general, when we have a general material model, we can represent this whole thing as just one function. Everything that's inside these parentheses here, we can think of this as just this one function that sort of determines the light reflectance off of the surface. So this is going to be a reflectance function, and that reflectance function is going to receive the incoming light direction and the outgoing light direction. So that tells us basically what percentage of the incoming light coming from this direction is reflected in this direction. We're going to talk about this in a bit more detail later. So this is what's called a bidirectional reflectance distribution function, more specifically. We'll talk about it in a little bit. But let's try to understand what this material function, what this function is trying to model. Now, again, let's go back to things that we are familiar with. Imagine a teapot with some texture on it. So the one above here, the one at the top, is a diffuse material that has no specular reflections, as you can see. The one below, you should be able to see some reflections on this one, right? So it's more shiny and all. Now, let's forget about the shiny one. Let's think about this diffuse one first. Like, why is this looking diffuse? What does that even mean? So to explain this, I'm gonna show you a little piece on this surface. Let's pick a little piece on this surface, and I'm gonna extend it over here. Now, I'm going to zoom in a little bit. I'm going to pick a small section of this, and I'm going to enlarge it some more. Again, I'm going to pick a small piece, and I'm going to enlarge it. Anyhow, I'm just zooming into the surface. Imagine that way. So if you zoom in enough onto a real surface, you should be able to see that it's not going to be, at some point, it's not going to be perfectly smooth, right? There's going to be some variation on the surface, that the surface is not going to be perfectly smooth if you zoom in enough. Might be, the amount of variation on the surface depends on what kind of material we're looking at. So in the end, if we have a diffuse material, what's going to happen is that when we have light coming from a light source, that's a beam of light coming from the light source, that light, depending on what exact point it hits on the surface, it's going to scatter in different directions, right? And if we have a diffuse material, that means that the scattering is going to be more or less uniform in all directions. So this beam of light hitting the surface, it's scattering in all directions uniformly if we have a diffuse material, right? So that's what it comes to. So when I look at this, when I look at a diffuse object, it doesn't really matter from which direction I'm looking at. I'm basically seeing more or less the same thing on average because light is scattering in all directions equally. But if the surface is not rough like this, if it's a more smooth surface, and when you zoom in, you can still see a surface that's really, really smooth like this, the scattering is not going to look like this, right? The scattering is going to look more like a mirror. So the light hitting the surface is going to bounce off in the same direction. If that is the case, and I'm looking at this surface, light is coming from that direction, I'm looking at from this direction, I am not going to be seeing anything, right? I can only see something if I'm looking at from this direction. Well, over here, I won't be able to see anything because no light is reflected towards me. All light is reflected in that direction. So a surface that is so smooth like this is going to have what we call specular reflections, and a surface like this will actually look like that, right? So as you can see, this specular highlight on the surface is changing direction. It's changing position on the surface based on from which direction we're looking at the surface, right? So directionality becomes really, really important. Typically though, a typical surface can have a mixture of these diffuse and specular reflections. So in this case, some light is reflected specularly and some light is reflected diffusely. So we see some diffuse color on the surface, but we also see some specular reflections, right? So there's some diffuse color, but there's also some specular reflections. And why is that happening? Now that would happen because this surface is not perfectly smooth. If the surface is perfectly smooth, that's not what's going to happen, right? This happens if there is some roughness to that surface, but it's maybe not that rough. So there's still some alignment. So I'm seeing some specular reflections, but it's not perfectly smooth. I still see some diffuse reflections in scattered in all sorts of different directions as well. Or it could be something like, oh, the surface has some flat parts and some parts have some roughness, right? It could be a mixture of these perfectly smooth pieces intertwined with some rough pieces in between. Or it could be a layered surface. So I could have a coating on the surface that's perfectly smooth or almost perfectly smooth. And then there's this underlying layer that is sort of rough where I see some diffuse reflections. Regardless of what this is, what you need to understand from here is that when the light comes and hits a surface, a part of it, it's going to scatter in all directions, and how it's scattered sort of depends on what kind of material we have on the surface. And this material reflectance function, or more specifically bidirectional reflectance distribution function, is going to try to define what the surface is and how it behaves, how the light reflects off of that surface. Right. So again, showing this specular version and the diffuse version of the teapot. Now, something is a little bit wrong here. So this one has diffuse reflections. This one has diffuse plus specular. But if I'm going to have specular reflections on the surface, that means the percentage of light that's reflected specularly will not be reflecting diffusely. Right? So a light is hitting the surface, a portion of it is reflecting diffusely, a portion of it is reflecting specularly, right? So if some portion of the light is reflecting specularly, and I'm seeing specular reflections here, so yeah, then that portion is not reflecting diffusely. That's what it means. So it means that my diffuse component should get a little bit darker if I'm going to have a specular component, right? And that's an important thing to understand. So when you look at the surface, you see that a part of it is reflecting diffusely, a part of the light is reflecting specularly. So as I have more specular, I'm going to have less diffuse. As I have more diffuse, I'm going to have less specular, right? We should think about it that way. So this is our setup. Light is coming and hitting the surface, and I'm observing it from a particular direction. And our bidirectional reflectance distribution function is going to define what percentage of the light coming from this direction will be reflecting along this viewing direction. Now, it's not saying anything about diffuse reflections or specular reflections. Now, the Phong and Blin material model explicitly separated the reflectance into diffuse reflections and specular reflections. And that's a good model for defining a lot of our materials, but it's not the only model. We don't have to necessarily separate diffuse reflections and specular reflections. What's important is that this function tells us what percentage of the light is reflecting along this direction that I'm looking at the surface, right? Along the viewing direction. What percentage of the light coming from the incoming light direction is reflected along this direction. So this includes both specular and diffuse and whatever else you might have in your material model. I don't care what it is. I just want to know the percentage. Okay? That's the general model. Now let's bring these terms to a form that is more generally used in the context of rendering equations. So I'm going to replace these terms. Instead of V here, I'm going to use omega O, and the outgoing light that I'm going to be seeing is going to be LO. Then incoming light is going to be omega I. Incoming light direction is going to be omega I, and incoming light is going to be Li. Symmetrical, as you can see, this incoming light direction, outgoing light direction, I'm using the same terms. One of them is I, the other one's O. Incoming light is I, Li, outgoing light is Lo. All right, so that's what I'm trying to compute with my bidirectional reflectance distribution function. So it will tell me, this function, bidirectional reflectance distribution function, is going to tell me for light coming from a particular direction, omega I, that light is coming from that light source and hitting this surface. And it could, if it's reflecting perfectly diffusely, it's going to be scattered in all directions in equal amount. But in general, for a material, it's not going to be quite like that. Light hitting the surface is going to favor some directions more than other directions. So in some directions, I'm going to have stronger reflections. In some directions, I'm going to have less reflections, right? And this function will tell me what it is. Now, an important property of this function is that this needs to add up to 1. What do I mean by that? Or it could be less than 1. So I look at all directions that this light is scattering. Right? If I look at all directions, if I sum the reflected light going to all directions, it should be less than or equal to 1. Because I cannot reflect more light than I'm receiving, right? This surface cannot reflect more light than it receives. So that means if I take an integral over this hemisphere of all directions above this surface, if I take an integral, that means I sum this function over this entire domain of the hemisphere. The result should be less than or equal to 1. That's basically saying that this function is energy conserving. So it's not adding energy. So it's not receiving some light and emitting more light. Now, this is very typical for most materials, but not necessarily all materials, actually. There are what we call fluorescent materials that can emit more light than they receive. But we're not talking about fluorescent materials. Typical materials will only reflect the light that they're receiving. All right. And we typically draw this function, this BRDF function, bidirectional reflectance distribution function, using a curve around this as a function around this all possible directions. So we don't draw these these arrows, but we represent it as a function like this. But of course, this is just one cross section of this function. This is not the entirety of this function. This is a particular shape that belongs to a particular incoming direction omega I. Right? If I change the incoming direction, this function will look a little bit different. Right? As I change the incoming direction, I have a function that looks a little bit different. So it's just one cross section of this function that takes two directions as input. What we want is the value, a single value of this function for the particular direction that we're looking at. So we're going to be looking at the value of this function for a given incoming direction and an outgoing direction. That's what we are interested in. Another interesting property of this function is that if I swap the order of incoming and outgoing, it won't matter. So for a realistic BRDF, it's going to produce basically the same result regardless of which order I provide these directions. So this means that I'm going to get the same reflectance value if the light is coming from this omega I direction and reflected on this omega O direction, or if I swap the order of the light and the camera, I should get the same value. Now, strictly speaking, this is not necessarily the case for all possible BRDFs. So you can come up with a BRDF model that is not going to provide this property. But for most BRDFs and physical-based BRDFs, this property is going to hold. Right? So either way, it's going to be the same. Regardless of what it is, though, what we want to do is that we want to compute this outgoing light. Right? The outgoing light towards the camera, that's what we're trying to compute. And how am I going to compute that? Very easy. I'm just going to look at the incoming light, multiply by the geometry term, and then multiply by the BRDF. Right? The BRDF will tell me what percentage of that light coming from that direction is going to reflect along this direction. And does this look familiar to you? This must look familiar. Even if you haven't seen the rendering equation before, this must look familiar because you've implemented this. We've done this. Remember, this was our shading function? So basically, it's the same thing, right? The outgoing color is this. The incoming light is this term, and the cosine theta and the BRDF terms, they're the same terms, right? So basically, this is what we've been doing. It's just written in a slightly different notation. So what happens if I have more than one light source in my scene? So this was just one light source, and that was relatively easy. It's just this. What if I have, let's say, a bunch of light sources in my scene? What do I do then? In that case, I'm going to have a sum. Because light coming from all of these light sources will reflect, and I will have the sum of all reflected light along this direction, right? So I'm supposed to have a sum of all lights. Again, the very same equation. All good? All right, let's take it to an extreme. Let's say that the light is coming from not just these few particular directions, but light is coming from all directions. All directions above a hemisphere contained, placed on top of this point, aligned with the surface normal. If the light is coming from all directions, then I'm going to have a sum over all directions, which means that it's going to be an integral over all directions, right? So omega I is going to be an integral over all directions, omega I, on the hemisphere. This capital omega is the hemisphere of all directions. All right, that is the rendering equation. That's what I showed you earlier. This is it. That's it, really. Light is coming from all directions, and we're just summing it up, and there you go. There's our result. Not too tricky, right? So let's get into it a little bit. Now, in the context of Blin-Phong shading, Blin-Phong material models, this was our material model. So in this case, basically this BRDF is just this function. So this BRDF function in this case has a diffuse term, which is constant over all directions, right? And a specular term, which sort of depends on the incoming light direction, right? So if I change the incoming light direction, the specular term is going to change position a little bit. So for both Blin and Phong material models, basically that's what they look like. But as I said, these are just two example material models. They're relatively simple material models. There are much more realistic material models we have today in computer graphics, a topic that I'm not planning to get into today. But we also have measured materials. So you can actually measure this function. You can measure the BRDF by shining some light onto a surface and measuring how much light is reflecting at a particular direction. And people have done that. We have some databases of different materials, and you can use those measured BRDFs for rendering and get materials that sort of do a very good approximation of actual material behavior. Did all of this come out of the University of Utah? Well, most of computer graphics came out of the University of Utah when you think about it. So the Blin and Phong material models, when they published them, they were in the University of Utah. I don't believe Jim Kajia was at the University of Utah when he published the rendering equation. He is a Utah grad, but I think he was a professor at Caltech when he published the rendering equation. But he's a Utah grad, so yeah, it came out of Utah. You can say that. We can claim credit. Why not? Yeah, I mean, if you if you try to look at the roots of everything that happened in computer graphics, eventually you'll find yourself in the University of Utah. That sort of makes sense. But yeah, it depends on how far back you want to go to. Okay, so these are some examples of measured BRDFs. We also have material models that are not measured. There are more realistic material models we have in computer graphics that are more frequently used than blend and foam materials today. But anyhow, this is enough about the BRDF for now. I want to go back to this rendering equation. And this is the important part about this lecture. This is the part that I would like to go a little slow. All right. So light is coming from all directions, right? And I am sort of summing all the lights. Basically, this integral means sum, a continuous sum of all light from all directions. When would I need something like this? For example, imagine light coming from the sky in a sort of cloudy day. Light is coming from all directions, right? So, it could maybe look like this. Well, okay, this doesn't look very cloudy, but you get the idea. Its light is coming from all directions, more or less equally, not exactly equally, but more or less equally in this case. So to be able to compute lighting like this, you kind of need to compute this integral. Now, I'm not telling you how to compute this integral. That's beyond what I plan to cover for today. But you understand that to be able to compute an image like this, you kind of need to compute this integral, right? You need to look at all light coming from all directions. But what if the light is coming from a single light source only? What if I have a single dominant light source in my scene, which is, let's say, the sunlight? I got rid of the sky here. I just have sun, all right? The sun is shining light on this teapot, and I have shadows on the floor and whatnot. So in this case, light is coming from, to some approximation at least, from only one direction. I'm treating the light source, the sun, as a very, very far and small light source. So only from one direction I'm seeing the sun. For all other directions, I'm not seeing anything. So if I look at this integral, for one direction and one direction only, which is the direction that corresponds to the sunlight in the scene, I am going to have illumination. For all other directions over this hemisphere, for all other directions, this incoming illumination, Li, is going to be exactly 0, right? Because I only have this one light source in the scene, which has a single direction, and that's where I'm getting my illumination. For all other directions, it's going to be 0. So, and if this function, incoming light function Li, is 0 for all other directions except for a single omega I, then this whole integral collapses to this, right? It's the same thing because all other directions are 0. So I can compute this integral very easily if this is the case. So there you go. This is what we've been doing for a single light source. And we've been doing it right, it seems. But what if I don't have just the sunlight, but also I have a sky that's sort of reflecting the light? And that's more typical, right? When think about a sunny day, we're going to have some strong sunlight coming from the sun, but we'll also have some light that is scattered from the atmosphere and it's going to be illuminating everything in the scene. So this is a more typical thing to look at. In this case, I'm going to have some light coming from the sky. Let me call this sky. So this is the light coming from the sky. I excluded the sunlight now. And on top of that, I also have the sun. So I can add it like so. So I have the skylight light is coming from all directions. I also have the sunlight. L sun is here is the sunlight, and this is the sunlight direction. And this term is giving me the sunlight. Now, this is just a different way of writing the same equation. This is not a different equation per se, it's just a different way of writing the same equation. So if I just combine this skylight function and the sunlight function into one lighting function coming from all directions, it would just be one function and one integral. This is, again, the same, very same rendering equation. Well, the important thing here is that I'm going back here. It's the same thing, right? This is the sunlight. This is the light coming from the sky. Sunlight is easy to compute. I know how to compute this. This is a little more difficult to compute because I kind of need to look at all directions. I mean, it's not that difficult, this one. It's doable if it's just coming from the sky. It's doable, but you know, it's not as simple as this one, right? This one is a lot simpler. So by taking this equation and splitting it into two components, such that I have the skylight and the sunlight, I am able to compute at least a part of this very efficiently and very easily. Right? So, and this is going to be a very typical thing to do. As much as we can easily write the rendering equation in this simple form like this, it's just one integral. Oftentimes, when it comes to computing the rendering equation, we're going to go ahead and start splitting this equation into multiple pieces. We're going to split it into multiple pieces so that we can compute that more easily. And it is important for you to understand how everything comes together in the rendering equation so that you're not counting things twice and not getting the wrong result. So it's important for you to, whenever you're in doubt about how to combine different things, always think about the rendering equation. Like, how would they fit in the broader context of the rendering equation? Now, let me give you another example, which is going to be important for the things that we're going to be discussing next week. Let's say that I don't have this boring diffuse material on the surface. Let's say that I have a more specular, nice, shiny teapot. All right, now look at this shiny teapot. Do you see the specular reflections of the sun? Is it on the edges up here? It's it's shiny, so it kind of looks, it's a little too shiny maybe, so it kind of looks a little small. But another thing that's happening here, now from this diffuse to more specular material, you see there's specular highlights appearing at the top, but at the bottom here something is happening too. You see the bottom part became a little brighter. You see that? It was sort of dark. It became brighter. Why is it becoming brighter now? What just happened? Well, maybe it's going to be a bit more clear if I add more objects to the scene. Let me add some hemispheres. You see what's happening? I added 2 hemispheres, and you're seeing the reflections of these hemispheres. Well, why not? So think about it this way. Light is coming from the sky, coming from the sun, and hitting a surface, and then it reflects and we see it. Right? That's why we've been computing. That reflected light is also light. It's light. Reflected light is light as well. So that reflected light can go and illuminate another object. So in here, when you look at the rendering equation, for certain points on this teapot, if you look at all possible directions over the hemisphere, some directions will contain light coming from these other objects in the scene. Right? So that's going to be the light coming from these other objects. So basically, these reflections that we see on the surface are nothing but just light coming from these other objects. So I can write the rendering equation like so. I can take this incoming light term and say that the incoming light term is the light that's directly coming from the light sources plus the light that's coming from the other objects. Right? So this is actually the light that's coming to any surface on this teapot. Right? And in this case, we are seeing the specular reflections of the sun because this is now a smoother surface, more clear specular reflections on the surface. So we can see the specular highlight of the sun, and we can see the reflections of the objects for the very same reason. It's still the same BRDF, right? I've changed the BRDF now that the BRDF is shiny, but both the light coming from the light sources and light coming from other objects, they are multiplied by the same BRDF, right? And because this BRDF is much more specular now I'm able to see these specular reflections of other objects, just like the specular reflections of the sunlight. Now, this is a very, very important concept, and this is going to play a lot of role in what we're going to be doing next. It's important for you to understand that these are the same things. Right? The light coming from the light sources, light coming from the objects, it's the same thing. But we are going to compute them differently. Because oftentimes you will see that light coming from the light sources directly, that's going to be a lot easier to compute. Light coming from other objects, that's going to be a little tricky. It's going to involve a lot more computation. So even though this one rendering equation up here includes everything, we're going to go and separate it into pieces and compute these pieces separately and then put everything together to compute our reflected light. All right, so a lot of our computation is going to involve separating this rendering equation into pieces and computing each piece separately using different algorithms. Now, in this case, when we think about light coming from the light sources and light coming from the objects, the typical name for them is going to be direct illumination, light directly coming from the light sources; indirect illumination, light coming indirectly from the light sources, that is, light coming from the objects. So what does that mean? That means the light is coming from the light source, hitting an object, and then reflecting off of that object and illuminating another object. So that's why it's indirect illumination. Another thing to notice here is that if I pick a particular direction omega, just pick one direction omega at a point on this teapot. From that direction, I'm going to have either indirect illumination or direct illumination, right? So if I have indirect illumination from that direction, I'm not going to have direct illumination because direct illumination will be shadowed by some object that's sending indirect illumination in that direction, right? So in that sense, we're not sort of counting things twice by adding them like this. So when we're computing this equation, the rendering equation, we're not going to try to compute it as one integral oftentimes, one integral that contains this combined illumination function, which is the sum of both direct and indirect illumination. Oftentimes when we're trying to compute this, we're going to separate it and we're going to compute direct illumination and indirect illumination separately. So I can write the same equation as a sum of two integrals, right? One integral is for direct illumination, the other integral is for indirect illumination. It's the same equation. But when I separate it like this, what this allows me to do is to use completely different algorithms for computing direct illumination and indirect illumination. Now, this is not specific to direct illumination and indirect illumination. We're going to be separating things quite a bit. Whenever it's convenient, we're going to look at these terms and separate them into pieces. We can even take the BRDF and separate it into pieces. We can say, I'm going to have an integral for one part of this BRDF, and I'm going to have another integral for another part of this BRDF if my BRDF has two terms. For example, For a blend material, I could have one integral for the diffuse component, another integral for the specular component if I want to. I'm not saying that I'm going to do that specifically. I'm just giving that as an example of something that I can do. And we're going to do tricks like this because computing certain things are going to be a lot easier than certain other things. And if you combine everything together, computing everything is going to be complicated. But if you separate this integral into little pieces, we can maybe handle some of these pieces very efficiently, and sort of we can approximate the rest. So we're going to be doing tricks like this in the context of interactive computer graphics. So get used to that. That's going to be something that we're going to be doing. So computing this indirect elimination is going to be oftentimes a lot more expensive than computing the direct elimination here. Oftentimes we can compute direct elimination in a relatively cheap way. Computing indirect elimination is not going to be that easy. Now, direct elimination plus indirect elimination, everything combined, is what we call global elimination. We're going to talk about global elimination much later in this course. I'm going to talk about some real-time interactive global elimination computation techniques. So we're getting there, but that's not what I'm trying to get to today. I would just like you to be familiar with this equation and to understand that we're going to rely on this equation, but we're going to compute different pieces of this equation. And if we're omitting any of the terms, we must understand that we're just omitting these terms. For example, in our blend shading project, we've been computing direct elimination. Basically, we've been computing this integral. Well, you didn't have to compute an integral because light was coming from only certain directions. So this integral collapsed to light coming from one direction, right? So that turned out to be something super easy to compute. How about this guy though? Indirect elimination. We didn't have a term like this, right? What we had was the ambient term. So the ambient term was a gross simplification of this whole integral. So yeah, it was not a good approximation of this integral, but it was some term that sort of acknowledged the existence of some other term here. Pretty much it, really. But yeah, ambient term, basically it's an approximation of this sort of complicated and expensive to compute term. So let me move on to the next thing. We're coming to the end. So when you see the rendering equation in a lot of places, you will see this additional term here, this emission term. Because if the surface has some light emission, if the surface is a light source, it's going to have some emission as well. So this equation also includes light sources. So light sources can be written in this form. I mean, if the light source has a surface, it's going to reflect the light, right? It will also emit some light in certain directions. So there's going to be this emission term added to it. Another thing is that now this is accounting for the light over this hemisphere, right? Because light can come from only above the surface. If I have a surface and light can only come from above the surface, any light that comes from behind the surface is sort of ignored if the surface is completely opaque. What if the surface is not opaque? If the surface is not opaque, then that means the light coming from behind the surface will pass through, right? And there is going to be light coming from behind the surface in some cases. So in that case, we can extend the equation a little bit. And instead of this omega that represents all directions over a hemisphere, I'm going to write s squared here that corresponds to the lights coming from all directions over the sphere. S squared corresponds to the sphere of all directions. And I renamed my bidirectional reflectance distribution function. It was fr. I renamed it as fs. Now it's scattering function. That is bidirectional scattering distribution function. And the scattering can scatter light coming from any direction. It doesn't have to come from only above the surface. It can come from behind the surface as well. So this is a more general form of the rendering equation that's accounting for all directions over the sphere, and it's talking about scattering, not just reflection, any kind of scattering over the surface. So in that context, we're not just looking at this hemisphere where the light could be coming from, but we're sort of looking at all directions over the sphere. All directions over the sphere. And why would we need that? Here are two examples for you. One of them is what we call subsurface scattering over here. And the other one is refractions. So refractions, if you have a transparent surface, it's going to have some refractions. And the refractions will be light coming from behind the surface, right? So it can be considered in the same context. Now, subsurface scattering is a little bit different. So this is, again, light coming from behind the surface. But in this case, light is sort of, if you think about this gummy bear, maybe? Light is scattering inside the volume of this object. So inside this volume, light is sort of bouncing off. And that actually happens a lot in reality. So if you shine a piece of light on your hands, you'll see the light coming from the other end. So the light will pass through your fingers and you will be able to see it through. That happens a lot, actually. And it's very, very important to give a realistic appearance of a lot of materials, and skin is definitely one of them. For character models, for example, ears are very important. So if there's light coming from behind, that's going to eliminate the ears from behind. But it's not just that. This subsurface scattering also includes light that's, let's say, in my arm, light is coming from above the surface. It penetrates into the surface and scatters inside this this volume below the surface, and then comes out from some other direction. So it goes in, scatters inside, comes out from another direction. So it's not always coming from behind, it's coming from the front, but it's scattering inside and then coming from behind. Like, there are that type of subsurface scattering events as well. And yeah, all of that is included in the context of subsurface scattering. So refractions are a little bit simpler than subsurface scattering, but it's sort of very, very closely related. And if you write the rendering equation in this form, where we're looking at all directions, not just the directions over the hemisphere, and we're considering bidirectional scattering distribution function, we're sort of including everything in here. And emissions. Okay, so this is what I plan to talk about today. Hopefully this was an extensive enough introduction to the rendering equation. And it is important for understanding all the stuff that we will be doing next. So when we're talking about reflections, which is going to be our topic for next week, try to think about them in the context of the rendering equation. So whenever you're unsure about how you combine certain things, just try to think about how these pieces would fit together in the context of the rendering equation. I think that's a very, very good tool for understanding how everything sort of comes together. But again, we're going to take that big equation, we're going to split it into pieces, and we're going to be computing each piece separately. So there's going to be a little bit of that going on starting next week. Once again, thank you all for coming to this lecture. Thank you, and good luck with the upcoming project. Hopefully you won't have too many problems with that one. And I'll see you all next week when we're going to start talking about reflections. Bye.